Kind of getting over a cold, so if I can't talk loud enough, just let me know. I'm going to talk louder. So has anybody heard of this before? Yes. What do you know about it? I forgot. It's some big number. Forgot. That's good. Okay, so we're all starting to roughly the same place. Yeah, the mole is an important concept in chemistry because it's how we transition from really small stuff to really big stuff. It's using this particular number. So let me show you what that means. Let's look at a chemical reaction, like one of the ones that we're going to do today. I think this is one of the ones we're going to do today. We're going to take solid magnesium and react it with oxygen gas. And we're going to get this product, magnesium oxide, which is a solid. So last time we talked about how you have to balance this equation. So we would put a 2 here to balance the oxygens and then a 2 here to balance the magnesiums. Hopefully some of your practice with that is going well or has gone well over the weekend. We'll have a quiz on Thursday. Just to remind you again that we'll cover some of this balancing equation type stuff, not the stuff we're talking about today, the stuff from last week. So anyway, we balance this equation, and we talk about how that brings it into balance in terms of the masses, in terms of the numbers of atoms. We really talk about what that means from a chemical reactivity standpoint. And what I'm saying is that this literally means that in order for this reaction to work, you need 2 magnesium atoms and 1 molecule of oxygen. You know, you can think of them almost like ingredients of some sort. Here's your magnesium atom. Here's another one. I don't know why I drew a circle around it, but that's fine. And then here's our oxygen molecule. We'll draw a circle around that too. So we need 2 magnesiums and 1 oxygen molecule to get this reaction to work. That's what this is saying. And then for our trouble, we will produce 2 magnesium oxides. Whoops. We're not going to use a line between magnesium and oxygen because that's an ionic compound. We'll just say like 2 of these compounds. If we imagine each of them is just being 1 atom and one atom of magnesium, 1 atom of oxygen together. So we can think of those numbers out in front of the formulas, not just as some sort of abstract number to balance things out, but as an actual count of how many of each thing you need. Anybody make any recipes recently? Or compared to a recipe, what did you make? Alfredo pasta. All right. So to make Alfredo sauce, you need butter, flour, milk, cheese. No. I'm just throwing it out there.
It was like cream.
Heavy cream, okay. Parmesan cheese. Okay. And so in order for that, so I'm going to stretch things a little bit here, but in order for that to come together, you needed a specific amount of each one, right? So like, maybe it's not quite as precise as what we might need in chemistry, but certainly like if you had way too much cream, it would be watery and it wouldn't come together right? This works especially with like baking. If you're making cookies or cake, if you're a little bit off in your ratios of ingredients, the whole thing's gonna fall apart. Anybody have any good stories of like baking failures where something just did not work? Forgot to put eggs in something, so what happened?
Oh, yeah.
Do you remember? Okay, it's something bad. It wasn't good, right? Yeah, it didn't work. What about yours?
I put baking soda instead of baking powder.
Oh yeah, that doesn't work. Yeah. Yeah. So like if you don't put it all together in the right ratios, it doesn't come together. Any other good ones? Anybody like make their family sick or anything? Like not like in a dangerous way, just like in a fun way. Yeah, me neither. The worst I did was I was cooking at somebody else's house, and I thought I was putting powdered sugar over the top of a cake, but it was actually baking soda. It didn't mess with the recipe, but it tasted really gross because baking soda is really bitter. Yeah, that wasn't good. I was like trying to wipe it off, and it wasn't good. So anyway, point being that you need to have your ingredients in the right ratio to make the right amount of stuff. And that's what balancing the equation tells us. But at this level, this is not actually really useful to us because we can't count individual atoms and molecules. They're just too small. You can't take out little tiny tweezers and count 2 magnesium atoms to react with 1 oxygen molecule. So we have to find a way to be able to count things that are really small without actually counting them one by one. Any idea how we might do that? How do you count things that are really, really small if you can't actually individually count them? But
You guess.
you guess. So that's one way to do it. Probably not the most successful, depending on how good you are at guessing. But there's other ways to do it, like if you had a giant jar full of jelly beans. So it doesn't even have to be that big. You have like a big bag of M&Ms or something. You want to know how many M&Ms are in that bag. Let's say, it's a huge, huge container just filled with M&Ms. How do you figure out how many M&Ms are in there? Okay, but what if you actually want to know how many M&Ms are in there? Okay, but what if you don't want to, what if that takes too long? Is there any other way to do it? If they're science?
Size.
Oh, size. Yeah, what do you mean by size? Do you want to? You could weigh it. So like if you had a thing with thousands and thousands of M&Ms in them, and you didn't want to count everyone out, what you could do is you could weigh 1 M&M, and then weigh all the M&Ms, and divide those 2 numbers, and you know how many you have. Food manufacturers do this all the time by estimating how many are in a bag. Like when you get a bag of M&Ms, it doesn't say how many are in there, right? But it says the weight. So they know how many are in there, but they're doing it by weight because it's a lot easier than having to count out a bunch of little tiny things. And so that's what we do with molecules. We can't count them because they're too small. So we have to weigh them. And how much does an individual molecule weigh? Well, we can't really weigh that because it's too small, but we have some numbers that can help us. So we can say that a magnesium atom weighs, we look up in the periodic table and we can say it weighs 24.3 AMU on average. Okay, we could have just rounded that to 24, but I didn't want to confuse this. Remember we talked about mass numbers before, that's a little bit different. We're saying if we average all the magnesium atoms together, in general they weigh 24.3 AMUs. AMU means atomic mass unit. It's this tiny little unit that is only really used for atoms. So we can weigh that, and we can weigh a whole bunch of magnesium atoms and then find how many are in there. The problem is they're so small that any amount that you could actually realistically weigh would be many, 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 many magnesium atoms. Somebody? Hey.
Sorry, you never know when it's open.
Okay. I thought you just weren't sure if you were in the right room or not.
Yeah.
That happens a lot up here. All the rooms kind of look the same. People just wander into other rooms because they are in the wrong spot. All right, so magnesium atom weighs 24.3 AMUs. That's not a super helpful unit to us. So a long time ago, somebody came up with this number, a guy named Avogadro, so it's called Avogadro's number. And if we have a whole bunch of magnesium atoms, specifically about 6 times 10 to the 23rd, which, if you don't know scientific notation, that means a 6 with like 23 zeros behind it, which is a huge, huge, huge number. But if we take that many magnesium atoms, we would say those weigh 24.3 grams. And now that's a unit we can actually deal with. So that number is ridiculously huge. That number is not really helpful. But by counting that many of them, we can get to a mass that is actually helpful, because you can weigh out 24.3 grams of aluminum. That's like a good handful or so of aluminum. Or magnesium, sorry, magnesium. So that's something that we can actually measure. So if you think about what that means, that allows us to count magnesium atoms by weighing them. To say, if we get 24.3 grams of magnesium, we know how many atoms are there. And so if we wanted to react it with oxygen, we could get a similar quantity of oxygen, depending on what we were trying to do. So that particular number has a special name because it works throughout the periodic table, and that's what we call the mole. So 1 mole of something, and let's actually write the number out because it's really big. So that would be 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 3. That's the number. And there's actually a few more digits past the first 3, but we'll just stick to 3 significant figures for now. So if you have a mole of something, you have that many of those things. It's just a name that corresponds to a particular number. And this is that particular number. We usually write it in scientific notation because it's a little easier than writing that whole thing out all the time. And the best way to think about what that means is if we use the exact same construction with a number that we know. If we said a dozen of something, how many is that? We know? 12, right? So the idea of that word, the mole, is the same thing as the dozen. If you have a mole of something, you have that many of them. If you have a dozen of something, you have that many of them. The number changes, but that's the idea. It's not a unit, it's not a measurement, it's just a number of them. Okay, so how do we use this? Well, because individual atoms aren't really something we can deal with, we like to often think about counting molecules and atoms using moles instead of using individuals. So instead of saying 12 magnesium atoms, we might say 12 moles of magnesium atoms. It's like if we go back to our candy example, if you didn't want to always be talking about individual M&Ms, you might talk about bags of M&Ms. And you can have a bag, or you can have 2 bags, or you can have half a bag, or you can have 2.5 bags, or whatever. So you can use that quantity to then bring you from the small to the manageable or large capacity. So we can talk about how many moles of a particular atom we have. I'll leave this up here so we can see it. So if we know that 1 mole of magnesium atoms weighs 24.3 grams, we can use that like a conversion factor to do some calculations. So we'll stick with magnesium so we have the same numbers. So 1 mole of magnesium, we look up at that red number on the periodic table, and we see that it weighs 24.3 grams. And so this brings us all the way back to chapter 2, where we have an equality. We have 2 things that are equal. And so from that, we can make a ratio and then use that to do some conversions or change some things. So 1 mole of magnesium is 24.3 grams of magnesium. Another way we could write that is as one of these ratios, 24.3 grams of magnesium per each mole. And sometimes we leave that E off the end as an abbreviation. It's not a great abbreviation. You just lose 1 letter, but that's how it goes. So that starts to look just like those conversion factors from back in chapter 2. So now we can answer questions like this. How many moles are in 43 grams of magnesium, or how many individual atoms is that? So, but with just a weight and some of this information from the periodic table, we can actually count how many magnesium atoms we have. So let's do that. The best way I think to do this, although if you've got your own way, that's fine. The way I like to do this is to treat it just like those problems from chapter 2. Think about your units. Think about what unit you're starting from and what unit you're going to, and then set up your equation and cancel units that way. So we would say, here we're given grams, and we're going to moles. That's what the question's asking, because it says how many moles are in 43 grams of magnesium. So we set up our gram to mole conversion. We'd start with that 43 grams and set up one of these conversion things just like any other kind of unit, where we're going to go from grams of magnesium to moles of magnesium. So setting that up with the units allows us to cancel that. I encourage you to keep the element name in that unit, because what we're going to do next is go from between different elements. But this is the basic setup. So we're canceling grams, and we're left with moles. All right. So then the next step is, what numbers do we fill in there? So what numbers do we fill in there? Yeah, so we look up on the periodic table, and those red numbers tell us how many grams are in 1 mole. So we can use that equivalence that we just found to say that there are 20. Oh, close me out. Oh no! Come on. Okay, well, computer broke. Can I do it with the mouse? This isn't going to look good. 24.3 grams in 1 mole. So it's that equivalence from before. At least we can finish that. Oh, there it goes. All right. Back. Okay. Now we can complete that calculation. (43 divided by 24.3). About 1.8 moles of magnesium. So 43 grams of magnesium is about 1.8 moles worth of magnesium. And the reason that's such an important conversion for us is that allows us to count magnesium by weighing it. So we can weigh 43 grams, and then we can know how many magnesiums are there. So let's do the second part of this question. How many individual atoms are there? Now, this is not a terribly useful calculation. In the actual lab, we won't do this much. It might show up on an exam here or there, but I'm not a big fan of this because it's just not that useful for a working person. So let's answer it. How many individual atoms? So to get the individual atoms, we want to convert from moles to individual atoms. So that's going to be 1.8 moles. Then we've got to convert from moles of magnesium to individual atoms. And for that, we use that definition of moles. So how many of anything are in a mole? It's that Avogadro's number, 6.02 times 10 to the 23rd. And it's always that number. It doesn't matter if it's magnesium, doesn't matter if it's atoms or molecules or donuts or M&Ms or whatever. That's how many of them are of anything are in 1 mole. So we calculate that out. Now this is the only time really that we've used scientific notation and that you essentially have to use scientific notation because the numbers are so big. So since we don't use scientific calculators in this class, at least you're not required to, how do you deal with those big numbers like 6.02 times 10 to the 23rd? How do you put that in a calculator like this? Or like those ones we use for the exams? Anybody know? That is just for squared on this calculator. And the other calculators don't even have that. So what you can do is you can, because it is a special thing called scientific notation, but it is also multiplication. It's literally 6.02 times 10 to the 23rd. So you can just multiply the number parts and then just stick the 10 to the 23rd onto the end. So we would go 1.8 times 6.02, forget about the 10 to the 23rd thing, and get 10.8 times 10 to the 23rd atoms. Now, proper scientific notation, if you're worried about it, says that you adjust your decimal place so that there's only ever one digit before the decimal. In this class, it doesn't matter. But if it's important to you, you can also write this as 1.08 times 10 to the 24th. If you are using a graphing calculator or a scientific calculator and you actually type in the whole number with the 10 to the 23rd, that's what it'll give you as the answer. Those are the same. Those mean the same thing. And for me, I don't care which one you report if you need to report that for an answer. So we did a couple of quick conversions, and we were able to weigh some chemical and then know exactly how many of them there were. And that's important if we go back up to these, back up to this equation. The balanced equation tells us the count. It tells us we need 2 of these for 1 of these. It doesn't tell us anything about weight. It doesn't say you need twice as much mass of magnesium as O2. And in fact, you don't. It'll end up being about the same. So we need to use this idea of the mole to figure out how to balance these equations in a practical way, like in the lab. So let's try that. I'm going to redraw the equation just so we have it again. So that's 2 mg plus O2 is 2 mgO. And we're going to answer another question using moles. How many moles of O2 are required to react with, let's use that same number from before, 1.8 moles of magnesium. So let's say we've got that amount of magnesium that we started with before, and we want to know how much oxygen do we need to add in. So if we just had individual magnesium atoms, that would be easy. We count out our magnesium atoms. It's 2 to 1, so we'd use half as many oxygen atoms, or oxygen molecules. When we're dealing with moles, it's actually the same thing. So we can set up a what's called a molar ratio between any 2 reactants in an equation, where we look at the ratio between these 2. So for instance, between oxygen and between oxygen and magnesium. That would be a way to look at a molar ratio. So how many moles of one do we need for how many moles of the other? And the nice part of that is you get those numbers directly from the equation. So you need the balanced equation, but then that's it. You just drop those numbers directly in there. So there's a 2 here for magnesium. That goes here. There's no number here for oxygen, but that means 1. So we put a 1 there. So our molar ratio is 1 mole of oxygen to 2 moles of magnesium. And that way we can set up a similar conversion to what we've done before to figure this out. So to answer this question, we go, all right, we're going to start with 1.8 moles of magnesium. And we're going to multiply that by the molar ratio, the thing that allows us to cancel moles of magnesium and instead get moles of oxygen. Those numbers are 2 for magnesium and 1 for oxygen, right from the equation. Just drop those numbers in from the equation. So our answer becomes 0.9 moles of oxygen. All right, I'm going to ask you another question. See if you can figure this one out using a similar technique, or same technique really. This time I'm going to ask you about the product. How many moles of magnesium oxide, MgO, are formed from the reaction of 1.8 moles of magnesium? So this is the same question as before, but instead of trying to find the quantity of oxygen, we're going to try to find the quantity of magnesium oxide. But you use the same technique. So see if you can do the same thing on your own, following the example of what we just did, but this time looking for magnesium oxide instead of oxygen. Then we'll look at it together and see if we found the right thing. So you should have to change like one number from what we did before to this one. right, did you get a chance to play with that a little bit? So to show you how this is the same, I'm going to copy the same thing over, and then we're going to talk about how we would change it. So I'm going to take this whole thing that we just did, copy and paste it, move it down here. Get rid of my arrow here. Okay. So if you look at what we did before, we were being asked for moles of O2 after being given moles of magnesium. This time, we're asked for moles of MgO after given those same moles of magnesium. So what changes in our expression here? What's the difference from what we did before? Yeah, we're just changing the molar ratio. So instead of looking at the ratio between oxygen and magnesium, we want to know the ratio between MgO and magnesium. And the equation gives us that that is 2 to 2, because there's a 2 in front of the MgO, and there's a 2 in front of the magnesium. So then here, that's again what changes. And then our product is what we're being asked for, MgO. So evaluating that, you could calculate it, but you could see that 2 divided by 2 is just 1. So that's actually going to be the same. So our answer is 1.8 moles of magnesium oxide. So in a chemical reaction, in a chemical equation, you can use the coefficients to come up with a molar ratio, which means if you know how many moles you want of any one of the parts of a chemical reaction, you can also find all the other ones just by doing a molar ratio of each one. Okay. So we'll practice this in a minute. What happens now if there are instead, if we're dealing with compounds? So we've looked at these individual atoms, these Mg. What happens if you have some sort of a larger compound? For larger compounds, we can come up with something called a molar mass. So molar mass is just that number that we looked up on the table for magnesium earlier, that 24.3. How many grams are in a mole? So it's always going to be grams per 1 mole. But in a compound, there's not just one thing. So let's say we have sodium carbonate, Na2CO3. So now we have not just one thing, but several things. How do you think we come up with how much a mole of that weighs? Ideas? If you had to guess? What? Yeah, we can do them all individually. So how much does 1 mole of Na2CO3 weigh? We're going to add up the individual amount. So we can say that there are 2 NAs in here, 1 C, 3 O. So that means we're going to multiply 2 times the mass of sodium, which we'll just round to the whole numbers. 1 times the mass of carbon, 3 times the mass of oxygen. Add all those together, and that's our mass of sodium carbonate. So 48 plus 47 plus 12 is 107. So that means that for sodium carbonate, there are 107 grams per 1 mole. Same kind of conversion factor, but this time we just have to add up all the individual components. Okay. What if you have something like this? What do you do with the molar mass of that? What? Yeah, you got to figure out all the stuff that's there. So you've got a CO. And then how many nitrogens are in that formula? 3, yeah, because you got to distribute that 3. And how many oxygens? Right, there's going to be 9, because you've got 3 oxygens in each nitrate, and then 3 nitrates. So that's 3 times 3 is 9. So go ahead and solve that one. Come up with the thing. Anybody come up with it yet? So what'd you get? 245. So for cobalt nitrate, we got 245 grams per mole. Some other things we could do with compounds like this. We're going to stick with those 2 that we've talked about. We can answer questions like this. How many moles of just oxygen are in 2.5 moles of cobalt 3 nitrate? So if we're just interested in the oxygen, we once again have to think of a ratio, have to use a molar ratio. We can think of it in words. It can be helpful to think about it in words, to say something like, there are 9 oxygens in each formula unit of the compound, which is what we figured out before when making the molar mass. That's another way of saying that. So in saying that, we've really come up with our ratio right there. There's 9 O's, 9 oxygens in each formula unit of CO and O33. So let's make that into a ratio and solve the problem. 2.5 moles of cobalt 3 nitrate. And then we want a ratio that cancels moles of cobalt 3 nitrate and instead gets us moles of just oxygen. So looking at the formula, we can say, well, there's 9 oxygens in each cobalt-3 nitrate. So that means that there's 9 moles of oxygen per each mole of cobalt-3 nitrate. If you ever get confused about this term mole, remember that you can substitute it for dozen, if you like that better, or just each, because it's just another way of counting things. If you say there's 9 of these in each one of these, that's the same as saying there's 9 moles of these in each mole of this. I mean, it's not the same, obviously, but calculation-wise, ratio-wise, that has the same kind of a relationship. So if it confuses you to think about the molar ratio, you can think about the individual pieces and how many of these are there in each unit, each formula unit. And that works as well. So if we evaluate this, 2.5 times 9 is 22.5. So there's about 23 moles of O in 2.5 formula, or 2.5 moles of the formula, the compound. All right, so as you see, being able to answer these questions requires that you can write down the correct compounds and that you can balance the equation. So for the next little bit, let's look at some problems that kind of bring in all this stuff together and how you could answer some of these kind of bigger problems using these ideas of moles. All right. Oops. Let's start with this one. Solid aluminum metal reacts with copper 2 nitrate to form aluminum nitrate and copper metal. How many moles of copper 2 nitrate are needed to react with 1.7 moles of aluminum? This is a big problem. A lot of writing. Solid aluminum metal reacts with copper 2 nitrate to form aluminum nitrate copper metal. How many moles of copper 2 nitrate are needed to react with 1.7 moles of aluminum? So it can sometimes help to just pick out the things you're being asked here. So the question is how many moles of copper 2 nitrate? And the thing that you're given is 1.7 moles of aluminum. So what do you need to be able to answer that question? What? You need to write it down. What kind of information do you need? Yeah, you need to know like what the molar ratio is so you can figure out how many moles of this do you need per each mole of this, or per how many moles of this. So you need those coefficients from the balanced equation. The only way to get those, of course, is to write down a balanced equation. So the first thing to do is write a balanced equation. Go ahead and try that. And if you get that, continue on and see if you can calculate the molar ratio.
this case, let's say how many moles of
But keep working at it if you're working at it. I want to put down the equation up here just so if you didn't get that, you can start working on the other parts of it. All right, so that's the balanced equation. And as you probably found, you had to put the compounds together properly to be able to get the right balanced equation. And then you need the right balanced equation to do the next part. So if you're still having trouble with writing down the right formulas for those compounds, make sure you review that. If you're having issues with balancing the equations, make sure you review that also. It all kind of builds on everything from before. Yep. All right, so for the next part, what we're going to do is use those coefficients from the balanced equation to come up with a molar ratio. And that's going to work as our conversion factor. So we're going to say, okay, we're given 1.7 moles of aluminum. And we want to convert that from moles of aluminum 2 moles of copper 2 nitrate. So the numbers we use there are directly from the balanced equation, 3 and 2. And we can evaluate that that's not right. Hold on. 1.7 times 3 divided by 2. There we go. So to come up with that last number, we had to write down the compounds from their names, put them in a balanced equation, and then use the coefficients from the balanced equation to come up with that molar ratio. So it's a lot of stuff. This kind of thing definitely takes practice. So make sure that you're doing all the homework so that you have plenty of practice on this before we do a quiz next week. Let's keep looking. Let's keep working on it for the rest for a little bit more time before we lab here. Similar question. We'll just use a different reaction. Solid calcium carbonate decomposes when heated to form calcium oxide and carbon dioxide gas. How many moles of calcium carbonate are needed to produce 23.3 moles of carbon dioxide? It's really the same type of question, just different reaction, different kinds of numbers. But once again, you need to put together a balanced equation and go from there. All right, let's take a look at this one. Once again, we need those compounds. In this case, there's just going to be one reactant on the left, calcium carbonate, because as the description says, it decomposes to form calcium oxide and carbon dioxide gas. We could put the states in there too, but not important for this right now. Okay, now we need to balance it. So we look at it, we count everything up, and in fact, this one actually is balanced just like that. Doesn't need any other numbers. We're going to do this reaction today in a little bit, by the way. So then for the next part, how many moles of calcium carbonate are needed to produce 23.3 moles of carbon dioxide? So we start with that 23.3 moles of carbon dioxide. And then we want a ratio that tells us the relationship between the moles of carbon dioxide and the moles of calcium carbonate, which is what the question asks for. In this particular reaction, that ratio is 1 to 1. Since we don't need to put any other numbers in there to balance it. So that means the answer is just 23.3 moles of calcium carbonate. All right, questions about that? No, all good? Okay, let's stop there and get ready for lab. So today we'll be doing, is it lab 6, right? Yep, the chemical reactions. So go ahead and take a look through the instructions, finish up your pre-labs, and we'll start up at 2.